Jupiter is not what you think. For centuries, we've called it a gas giant, imagining it as nothing more than a colossal ball of swirling vapors suspended in the void. But that image is incomplete, a sketch when we need a portrait. Jupiter is not a giant ball of gas, it is a liquid planet. And not just any liquid. Deep beneath those mesmerizing cloud bands lies an ocean of liquid metal, a substance so exotic that it exists nowhere else in our solar system in such abundance. Beneath those iconic swirling storms and amber clouds lies one of the deepest, most profound mysteries in planetary science. What we see from Earth is merely a veil, a thin atmospheric shell concealing an interior so strange, so extreme, that it challenges our understanding of matter itself. The first glimpses. The story of truly seeing Jupiter begins in 1974, when humanity sent its mechanical ambassador into the outer solar system. Pioneer 11 swept past the giant planet and captured the first close-up photograph ever taken. It was grainy, pixelated by today's standards, but revolutionary. For the first time, we could see Jupiter not as a distant point of light, but as a world. 5 years later, in 1979, Voyager 1 approached and gave us something even more remarkable: movement. The spacecraft recorded a time-lapse sequence showing the planet's clouds churning and rotating, vast atmospheric rivers flowing across a canvas larger than anything on Earth. Watching those images, scientists felt both wonder and frustration. The visuals were breathtaking, yes, but they answered almost nothing about what Jupiter truly was. Instead, they raised more questions. What forces drove those storms? What lay beneath the clouds? How did this colossus come to dominate our solar system? A giant among worlds. Understanding Jupiter begins with grasping its sheer scale, and that scale is genuinely difficult for human minds to comprehend. Jupiter is not just big, it is heavier than every other planet in the solar system combined. Saturn, Uranus, Neptune, Earth, Venus, Mars, Mercury, take all of them, add up their masses, and Jupiter still tips the scales. The volume is equally staggering. You could fit 1,000 Earths inside Jupiter's volume and still have room left over. To bring this down to something more tangible, imagine Earth shrunk to the size of a grape, small enough to hold in your hand. Jupiter, on that same scale, would be a basketball compared to a grape. That is the reality of the size difference we're dealing with. Standing on Earth and looking up at Jupiter in the night sky, it's easy to forget that this bright dot is a world so massive that its gravity shapes the entire architecture of our solar system. Theories of formation. How does something so immense come into existence? The leading theory begins with the birth of the solar system itself, roughly 4.6 billion years ago. Picture a vast disk of material, a swirling cloud of gas, dust, rock, and ice, all orbiting the newly ignited sunday. In the beginning, this disk was chaotic, with countless particles colliding, sticking together, building up. Over millions of years, these collisions created larger and larger clumps. As these clumps grew, their gravity strengthened, pulling in even more material. This process, called accretion, is how all the planets formed. But Jupiter took it to an extreme. According to this theory, somewhere in the outer solar system, one particular clump grew so large that its gravity became powerful enough to capture not just rock and ice, but the abundant hydrogen and helium gas swirling through the protoplanetary disk. Once it started, the process became self-reinforcing. More mass meant stronger gravity, which captured more gas, which added more mass, and so on, over hundreds of millions of years. This snowball effect built Jupiter into the giant we see today. If this theory is correct, then buried deep within Jupiter should be a solid core, a dense sphere of rock and metal, the original seed around which all that gas accumulated. But there's an alternative idea, one that's equally fascinating. What if Jupiter didn't form through gradual accretion? What if it began as a separate, enormous cloud of gas floating just outside the boundaries of the early solar system? In this scenario, that cloud grew so massive that it eventually collapsed under its own gravity, much like a star forms. Stars require much larger clouds to ignite fusion, but a cloud of intermediate size might collapse into a giant planet instead. Once formed, this nascent Jupiter would have been gravitationally captured by the Sun, spiraling inward until it settled into a stable orbit. If this theory were true, Jupiter would have no solid core at all. It would be layers upon layers of gas and liquid, a planetary layer cake with no hard center, just gradual transitions from one state of matter to another as you descend into its depths. For decades, the core accretion model was the dominant paradigm, the version taught in textbooks and classrooms around the world. It made intuitive sense, but as we'll see, intuition and reality don't always align. Jupiter, as it turns out, is far stranger than either theory predicted. A cosmic collision. The breakthrough in understanding Jupiter came in the mid-1990 seconds, and it arrived in the form of a celestial catastrophe. In July 1994, astronomers made a stunning discovery. A comet, later named Shoemaker-Levy 9, was on a collision course with Jupiter. Comet impacts on Jupiter are extraordinarily rare, estimated to occur perhaps once every 6,000 years. By sheer luck, or perhaps fate, humanity was alive during one of these events and possessed the technology to observe it. Shoemaker-Levy 9 was no ordinary comet. It was a massive chunk of frozen ice and rock, hurtling through the void at 216,000 kilometers per hour. By the time astronomers found it, Jupiter's immense gravity had already shattered the comet into more than 20 separate fragments, each one a potential impactor. The largest of these fragments measured about 2 kilometers across, a mountain of ice traveling at incomprehensible speed. NASA's Hubble Space Telescope, freshly deployed and operational, was positioned to observe the impact. But there was a problem. The fragments were going to strike Jupiter's far side, the hemisphere facing away from Earth. From our vantage point, we would see nothing. The once in 6,000 years event seemed destined to happen just out of view, except for one extraordinary coincidence. At the exact same time, NASA's Galileo spacecraft was approaching Jupiter. Launched in 1989, Galileo was on a mission to study the giant planet and its moons. Its arrival was scheduled for December 1995, but in mid-1994, it had a clear, unobstructed view of Jupiter's far side. Galileo became humanity's eyes for the collision. Over 6 days in July 1994, 21 separate fragments slammed into Jupiter. The largest impact released energy equivalent to 300 million atomic bombs, the most powerful explosion ever witnessed by human instruments. The fireballs rose thousands of kilometers above the cloud tops, visible even from Earth-based telescopes as bright flashes. As Jupiter rotated, Hubble captured the aftermath. Dark scars in the atmosphere, massive plumes of debris, shock waves rippling through the cloud bands. These impact sites persisted for months, some visible for more than a year. For the first time, humanity glimpsed what lay beneath Jupiter's clouds. The impacts had dredged up material from deeper atmospheric layers and ejected it into space, and Galileo flew directly through these plumes, analyzing their composition. The most surprising discovery was water. Lots of water. Not liquid water as we know it, but water vapor and ice mixed with ammonia and other compounds. The abundance of water was unexpected and hinted at a far more complex chemistry than previously imagined. This revelation set the stage for the next great mission to Jupiter, one designed specifically to probe the planet's hidden interior, the Juno Mission. That mission was Juno. Launched in 2011 and arriving at Jupiter in 2016, Juno represented a new generation of planetary exploration. Its instruments were designed not to study the surface, but to peer beneath it, using gravitational and magnetic measurements to map the planet's interior structure. What Juno found fundamentally changed our understanding. Almost everything taught about Jupiter in schools before 2016 was incomplete or incorrect because we simply didn't know. We didn't have the data. Now we do. And the picture that has emerged is astonishing. The cloud layer. Let's start at the top and work our way down, descending through the layers of this strange world. The outermost layer of Jupiter, the part we see from Earth, consists of thick clouds. These clouds are not made of water, but primarily of ammonia ice crystals suspended in an atmosphere of hydrogen and helium. The temperature here is brutally cold, around -100 degrees Celsius. Despite the cold, liquid water exists in the upper cloud layers, kept from freezing by ammonia acting as a natural antifreeze. Water droplets collide with ice crystals, building up electrical charge. The result is lightning, but not the lightning of Earth. Jupiter's lightning storms are titanic, bolts thousands of times more powerful than terrestrial lightning, crackling across storm systems larger than our entire planet. The clouds are in constant motion, Slushy hailstones, a mixture of water and ammonia, form in the upper clouds and fall into the warmer lower atmosphere. There they melt, evaporate, and rise back up in vast convective currents, perpetuating an endless cycle. These rising jets of hot gas fuel the storms we observe on the surface. The Great Red Spot, Jupiter's most famous feature, is one such storm. It has raged for at least 400 years, possibly much longer. The red spot is enormous, large enough to swallow 2 or 3 Earths side by side. But its size is only part of the story. The storm extends hundreds of kilometers down into the atmosphere, a churning column of ammonia, rain, and gas. It also rises higher than any other feature on Jupiter, towering above the surrounding cloud tops where it absorbs intense ultraviolet radiation from the sunday. This UV light reacts with chemical compounds in the storm, producing the deep crimson hue that gives the red spot its name. Imagine a storm system taller than 10 Mount Everest stacked vertically and deeper than 10 Mariana Trenches. Even that comparison fails to capture the scale. As spectacular as the cloud layer is, it represents only a thin skin, averaging just 50 kilometers deep. For a planet with a diameter of nearly 140,000 kilometers, this is negligible, a veneer. The real story of Jupiter lies far below. The hydrogen atmosphere. Descending below the clouds, we enter the lower atmosphere. Here, the temperature begins to climb. This may seem counterintuitive. Shouldn't it get colder as we move away from the sun's warmth? But the heat doesn't come from above. It comes from within, generated by pressure. Pressure, in turn, is created by gravity. Jupiter's immense mass pulls all of its material inward, compressing it. When you compress gas molecules, you force them closer together, concentrating their kinetic energy. That concentration manifests as heat. The deeper we descend into Jupiter's gravity well, the more intense the pressure becomes, and the hotter it gets. Hydrogen, the lightest and most abundant element in the universe, makes up the vast majority of Jupiter's mass. In the upper atmosphere, hydrogen exists as a gas, just as it does in the thin air above Earth. But as we go deeper, something remarkable happens. The fog thickens. The gas becomes denser and denser until it's no longer accurate to call it a gas. Around 1,000 kilometers below the cloud tops, the hydrogen undergoes a phase transition. It becomes liquid. This is not the liquid hydrogen we create in laboratories by cooling it to near absolute zero. This is liquid hydrogen formed by extreme pressure, existing at temperatures exceeding 1,000 degrees Celsius. We have reached the ocean of Jupiter, the largest ocean in the solar system. This ocean has no surface in the conventional sense, no clear boundary where you might say, here the atmosphere ends and the ocean begins. It's a gradual transition, a thickening continuum. But if we had to define a surface, this would be it. An ocean of liquid hydrogen stretching in all directions beneath a sky of hydrogen gas, under storms of ammonia and water. The ocean is approximately 20,000 kilometers deep, vastly deeper than Earth's ocean, which averages only about 4 kilometers. To put that in perspective, Jupiter's hydrogen ocean is 5,000 times deeper than the deepest point on Earth. Descending through this ocean, the pressure continues to build, the temperature continues to rise, and the hydrogen transforms yet again. The metallic hydrogen ocean, at a depth of about 21,000 kilometers, under pressures millions of times greater than Earth's surface, at temperatures around 10,000 degrees Celsius, hydrogen enters a state that doesn't exist naturally anywhere else in the solar system. It becomes metallic hydrogen. The term metallic doesn't mean it turns into a solid like iron or steel. It remains liquid, but its properties change fundamentally. Under such extreme pressure, the hydrogen molecules are crushed so thoroughly that electrons are stripped away from their atoms. These free electrons can now move through the liquid, conducting electricity just as electrons flow through metal wires. The liquid becomes a conductor, a vast ocean of metallic hydrogen capable of carrying electric currents. This metallic hydrogen ocean is enormous, making up the majority of Jupiter's volume. It extends roughly 40,000 kilometers deep. To understand what that means, consider that Earth's diameter is only about 12,700 kilometers. You could stack 3 Earths on top of each other and still not match the depth of Jupiter's metallic hydrogen layer. The existence of this layer has profound implications. Moving liquid metal in the presence of rotation generates magnetic fields, a process called a dynamo. Jupiter's metallic hydrogen ocean, churning and flowing in the planet's interior, generates the most powerful planetary magnetic field in the solar system, nearly 20,000 times stronger than Earth's. This magnetic field extends millions of kilometers into space, creating a magnetosphere so vast that if it were visible, it would appear larger than the full moon as seen from Earth. Now, if you haven't subscribed yet to Broken Zach, this is the perfect moment. We're diving deep into the cosmos, exploring the wonders of our universe, and there's so much more to come. Hit that subscribe button and join us on this incredible journey. The core. At the very bottom of Jupiter, beneath tens of thousands of kilometers of gas, liquid, and metallic liquid, lies the core. Or at least, what we think is the core. For a long time, scientists believed Jupiter's core was a compact, solid sphere about the size of Earth, composed primarily of rock and iron. This fit neatly with the core accretion model, the original seed around which the planet formed. But data from the Juno mission has complicated that picture. The core appears to be fuzzy. That's the term scientists use. Fuzzy. The transition between the metallic hydrogen layer and the solid core isn't sharp. There's no clear boundary. Instead, the two seem to mix together, creating a region where liquid, metal, rock, and heavy elements blend into a dense, hot soup. This fuzzy core spans roughly half of Jupiter's radius, about 35,000 kilometers across. It's not a small object. It's massive, containing several times the mass of Earth, but it's diffuse, with no well-defined surface. Scientists aren't entirely sure if this is unique to Jupiter or common among gas giants. We haven't studied Saturn, Uranus, or Neptune in nearly as much detail, so we lack points of comparison. If Jupiter's fuzzy core is unusual, one compelling explanation is a cataclysmic collision early in the solar system's history. Imagine a rocky planet 10 times more massive than Earth, wandering through the young solar system. It collides with Jupiter in a glancing blow, releasing unimaginable energy. The impact shatters and dilutes the core, mixing solid material with the surrounding metallic hydrogen, creating the fuzzy boundary we observe today. This collision might also explain how Jupiter grew so large, capturing additional mass from the destroyed planet. The collision theory is plausible and explains several observations, but scientists are cautious. Recently, researchers ran computer simulations to test the idea. They modeled collisions between a young Jupiter and planets of varying sizes and compositions. The results were surprising. Initially, the simulations did produce a fuzzy core, just as expected. But over time, the core would settle. Gravity would pull the heavier elements back together, re-solidifying into a defined sphere. The fuzzy structure was temporary, lasting only a few million years, not the billions of years since Jupiter's formation. So if Jupiter's core is still fuzzy today, the collision would have had to occur relatively recently, perhaps within the last billion years. But there's no other evidence of such a recent impact. No debris field, no leftover scars. The mystery remains unsolved. The unsolved mystery. This is the paradox of Jupiter. For all that we've learned, for all the data collected by Pioneer, Voyager, Galileo, and Juno, fundamental questions remain unanswered. How did Jupiter form? Did it build up gradually through accretion? Or collapse suddenly from a cloud? Why is its core fuzzy? What caused that structure? And why hasn't it settled? These are not trivial questions. They cut to the heart of planetary science. Understanding Jupiter means understanding how giant planets form, and that has implications far beyond our solar system. Astronomers have discovered thousands of exoplanets orbiting other stars, and many of them are Jupiter-like giants. If we can't fully explain the Jupiter in our own backyard, how can we understand those distant worlds? Jupiter's role in the solar system. But Jupiter is more than a scientific puzzle. It's also a guardian. Its immense gravity shapes the orbits of asteroids and comets, deflecting many that might otherwise threaten the inner solar system. The Shoemaker-Levy 9 impact was a dramatic reminder of this. Without Jupiter, Earth would face far more frequent bombardment from space debris. Some scientists believe that life on Earth might not have had the stable conditions needed to evolve without Jupiter's protective influence. At the same time, Jupiter's gravity has also been destructive. It likely prevented a planet from forming in the asteroid belt between Mars and Jupiter, scattering material that might otherwise have coalesced into another rocky world. Its gravitational influence may have flung countless objects out of the solar system entirely, shaping the architecture we see today, the Great Red Spot and other storms. Let's return for a moment to the Great Red Spot, because its significance extends beyond mere size. The storm has been observed continuously since the 1,830 seconds, and sketches by astronomers in the 1,660 seconds suggest it may have existed even then. That means the Great Red Spot could be nearly 400 years old, possibly older. On Earth, the most powerful hurricanes last days or weeks. Why does the red spot persist for centuries? The answer lies in Jupiter's structure. On Earth, hurricanes weaken when they pass over land, losing the warm ocean water that fuels them. Jupiter has no land, no solid surface. The storms never make landfall. They can rage indefinitely, sustained by the planet's internal heat and the energy of atmospheric convection. The red spot draws energy from temperature differences between the upper and lower atmosphere, a heat engine that never shuts off. But the red spot is not eternal. Observations over the past century show that it's shrinking. In the late 1800s, the storm was large enough to fit 4 Earths inside. Today, it's roughly half that size, enough for only 1 or 2 Earths. No one knows why it's shrinking or whether it will eventually disappear. Some scientists speculate that the storm could collapse within a few decades, while others believe it might stabilize at a smaller size. If it does vanish, it would mark the end of one of the solar system's most iconic features, a landmark visible from Earth through small telescopes for hundreds of years. Jupiter hosts many other storms, dozens of them visible at any given time. Some are smaller cousins of the red spot, anticyclonic ovals that persist for decades. Others are fleeting, lasting only weeks or months. High-resolution images from Juno reveal even more complexity. The poles of Jupiter, long hidden from view due to the planet's axial tilt and our perspective from Earth, are chaotic maelstroms. At each pole, massive storms are arranged in geometric patterns, cyclones clustering around a central vortex like petals on a flower. Why they arrange themselves this way is another mystery. The atmospheric dynamics that create these patterns are not fully understood, and they differ from anything seen on Earth or any other planet. The moons of Jupiter. Jupiter is not alone. It has at least 79 known moons, possibly more awaiting discovery. 4 of these moons are large enough to be considered worlds in their own right. Discovered by Galileo Galilei in 1610, these 4, Io, Europa, Ganymede, and Callisto, are called the Galilean moons. Io is the most volcanically active body in the solar system, its surface constantly reshaped by eruptions of sulfur and silicate lava. The volcanic activity is driven by tidal heating, the result of gravitational interactions with Jupiter and the other moons. Europa is covered in a shell of water ice, beneath which lies a global ocean of liquid water, one of the most promising places to search for extraterrestrial life. Ganymede is the largest moon in the solar system, bigger than the planet Mercury, and it has its own magnetic field, the only moon known to possess one. Callisto is ancient and heavily cratered, a relic of the early solar system, its surface recording billions of years of impacts. These moons are scientific targets in their own right, but they also tell us about Jupiter. The intense radiation environment around Jupiter, created by its powerful magnetic field, constantly bombards the moons. Studying how the moons interact with this radiation provides clues about the magnetosphere's structure and behavior. The tidal forces that heat Io and Europa reveal the strength of Jupiter's gravity and how it shapes the orbits of nearby objects. In many ways, the moons are laboratories for understanding the giant planet they orbit. Missions past and future. Humanity's exploration of Jupiter is far from over. The Juno mission continues to orbit the planet, collecting data and sending back stunning images. Each orbit reveals new details, from the structure of the atmospheric jets to the composition of the auroras at the poles. Plans are already underway for future missions. The European Space Agency's Juno Mission, short for Jupiter Icy Moons Explorer, launched in April 2023 and will arrive at Jupiter in 2031. Its primary targets are Ganymede, Europa, and Callisto, but it will also study Jupiter itself. NASA's Europa Clipper, set to launch in 2024, will focus specifically on Europa, conducting detailed reconnaissance of the icy moon and its subsurface ocean. These missions will not only explore the moons but also provide additional data about Jupiter's atmosphere, magnetosphere, and interior. One tantalizing possibility for future exploration is a probe that descends deep into Jupiter's atmosphere, much deeper than the Galileo probe did in 1995. Such a mission would face enormous challenges. The pressure and temperature increase rapidly with depth, and any probe would eventually be crushed and melted. But even a brief descent could provide invaluable data, directly sampling the atmospheric layers and measuring conditions that we can currently only infer. Concepts for such missions are being studied, though none have yet been approved or funded. The engineering hurdles are immense, but the scientific rewards would be extraordinary. Why Jupiter matters? Why does all of this matter? Why invest billions of dollars and decades of effort to study a giant ball of liquid hydrogen hundreds of millions of kilometers away? The answer is simple. Understanding Jupiter is understanding the universe. Jupiter is a laboratory for extreme physics, a place where matter behaves in ways that cannot be replicated on Earth. The metallic hydrogen that makes up most of its interior is a substance that exists nowhere else in the solar system in such quantities. Studying Jupiter teaches us about high-pressure physics, about how magnetic fields are generated, about atmospheric dynamics at scales unimaginable on Earth. Jupiter also holds clues to the solar system's history. The composition of its atmosphere is thought to reflect the composition of the protoplanetary disk from which the planets formed. By studying Jupiter, we're studying a relic of the solar system's birth, a sample of the raw materials from which everything was made. The planet's moons tell stories of impacts, volcanism, and perhaps even life. And Jupiter's role as a gravitational shepherd, shaping the orbits of asteroids and comets, has directly influenced the history of Earth. Without Jupiter, life on Earth might never have had the chance to flourish. Beyond our solar system, Jupiter-like planets are common. Gas giants orbit many of the stars we've studied, some even larger than Jupiter, some in closer orbits than Mercury. These so-called hot Jupiters challenge our theories of planetary formation and migration. If we can't fully explain our own Jupiter, how can we understand theirs? Every discovery about Jupiter informs our understanding of exoplanets, helping us interpret the data from distant worlds and refine our models of how planetary systems evolve. The weirdness of Jupiter. Jupiter is weird. There's no other way to put it. It's a planet with no solid surface, where you could theoretically fall forever, sinking deeper and deeper until the pressure crushed you into nothingness. It's a world where hydrogen, the lightest element, transforms into a metal under the weight of its own gravity. It's a place where storms larger than Earth rage for centuries, powered by heat from within and sculpted by forces we don't fully understand. It's a giant with a fuzzy heart, a core that defies our expectations and resists our attempts to explain it. And it's beautiful, a swirling canvas of colors and patterns, a testament to the complexity and wonder of the natural world. For all that we've learned, Jupiter remains a mystery. We've peeled back layers, gathered data, tested theories, and revised our understanding. But fundamental questions linger. How did it form? What's really at its core? Why does it look the way it does? Each answer leads to new questions. Each discovery reveals deeper complexities. And that's what makes Jupiter so compelling. It's a challenge, a puzzle demanding to be solved. It's a reminder that the universe is vast and strange, full of phenomena that defy easy explanation. And it's a promise that no matter how much we learn, there will always be more to discover. If you enjoyed this deep dive into Jupiter's mysteries, you're going to love our next video. It's a great one, exploring even more of the cosmos's most mind-bending phenomena. And with that, we'll see you in the next video.